Section 26.1 is about Galilean relativity, and the learning objective is to state and discuss the principle of Galilean relativity. According to the principle of Galilean relativity, the laws of mechanics must be the same in all inertial frames of reference. So before we go forward from there, let's talk about what it means to be an inertial frame of reference. And basically it just means in an inertial reference frame, the points are not accelerating. If you imagine a rocket ship that is accelerating, well, the points inside the rocket ship, the actual individual points in the rocket ship, are under acceleration. So in that case, the points are accelerating. So that would be a non-inertial reference frame. So while I'm mentioning this issue that Euclid said the points, or I'm sorry, that inertial coordinate system is one where the points are not accelerating. Let's take a moment to talk about Euclid's definition of the point. Definition 1 from Euclid's text on geometry was a point is that which has no part. However, I'm going to add a couple of things to that definition and say that for an inertial point, a point actually has duration, location, and velocity. So I give you a set of points here that are on my page, and you can see that those points had a beginning because they appeared at a certain point at a certain time in the video. I could erase them and then they would no longer be there. They also have location. Located in my presence, they're actually located on a sheet of paper. In your presence, they're located on a screen. And they have a velocity. Now for me, that velocity is 0. Although if I move my head a little bit, the velocity with respect to my head actually changes. But that's because my head is non-inertial because I'm accelerating it. Okay, but these points are more or less inertial. And then we have non-inertial points, which also have acceleration. So like if you drew these points on the side of an accelerating rocket, then those points would be accelerating. Okay, but back to the principle of relativity. The laws of mechanics must be the same in all inertial frames of reference. We can imagine a truck, and we are watching that truck, or we are watching from the point of view of somebody traveling next to the truck. And from that perspective, it looks like the person standing in the back of the truck throws the ball up and it comes directly back down again. On the other hand, if somebody is standing outside the truck and on the ground, then the truck is going by, the ball goes up in an arc and comes back down again. I'm going to talk for a moment about space-time diagrams. Here I've tried to draw a rudimentary drawing of that truck and a space-time diagram representing the situation. For the purpose of space-time diagrams, what you're doing is you're drawing position on one axis and time on the well, actually this is y, position on up to 2 axes, and replacing the third axis with time. But what I'm going to do here is I'm going to multiply time by a factor, because although I've drawn this as position, and time, I've labeled it time, what I've actually drawn is a distance in this direction. So in order that that distance be that distance related to time is calibrated with the distance in the x direction and the y direction, I just multiply it by a factor, which is a velocity. Here I'm using c as our velocity. So we got meters going to the right, we got meters going up into the page, and now we've got meters, velocity times time, going up this direction. And we've got what we've got is basically a stack of cards or photographs of the truck. So here the man is throwing the ball upward. Here it reaches its peak. Here the ball comes back down and reaches the man again. Now we can imagine what it looks like from the frame of reference of somebody standing on the road by just kind of like skewing those cards. So just basically taking them and slanting them and having an image here, an image here, an image here, an image here, an image here. And that is called the Galilean transformation of the cards. And I like to represent the transformations in a form that has a matrix representation. Here, we'll say x prime and ct prime is the view from the truck, and x and ct are the view from outside the truck. So what happens is we have our original x, or we have x prime, and then we multiply that by v over c times ct prime, or vt prime. And that gives us the position of that truck at any given time. So it's basically this times this is being added to this, so that every time, in every moment, that truck is a little bit further forward. So the way that looks is that those cards are basically being slanted, as you can kind of see in this. Imagine those cards being the dashed red lines here. And as I move this dot back and forth, or up and down, then you can see that those slanted lines just become more slanted. But also notice what happens to these purple lines down here. These purple lines in this diagram are supposed to represent the speed of light. Now what happens when I slant those cards, you end up getting different speed of light. And that is something that breaks the rule. Okay, it doesn't specifically break this rule. It says the law of mechanics must be the same in all inertial frames of reference. However, it breaks the rule that the laws of electromagnetism must be the same in all inertial frames of reference, because the laws of electromagnetism requires that the speed of light is constant. So in order to fix that, I'm going to go from Galilean to Lorentz and see what happens here. As I move this, instead of the cards staying horizontal, they are basically what's going on is there's a stretch and a compression along the axes of x equals ct and x equals negative ct. And especially watch what happens to those purple dots. Notice how that purple line does not change slope. It does not change slope. It does change how fast things are coming in. The distance between those dots changes, but the slope does not change. So that keeping the same slope means that the speed of light is preserved by this transformation. Then also look at what happens to this, let's say, this central line and these two lines next to it. So you can see that they just kind of are slanting. They're slanting, right? And the solid lines are slanting the same way with this one. The solid lines are slanting the same way. Okay, and that's good. The solid lines are slanting, because that is a similarity between the Lorentz transformations and the Galilean transformations, that those solid lines slant. What is different, what looks very different, is how the dotted dashed lines are operating. because in the Galilean transformations, those dashed lines do not slant. They remain at the same horizontal. They remain horizontal, but in the Lorentz transformations, they slant along with. Okay, and here's why. On this scale, the way I've drawn things is that the speed of light is 1. You'll notice the slope of this purple line is 1 or -1, and that's supposed to represent the slope for the speed of light. That means, for instance, if this is 1 second on the vertical line, then this would be 300 million meters, because the speed of light is 300 million meters per second. So we're not used to thinking in terms of scales of like where 1 second in this direction corresponds to 300 million meters in this direction, because our scale of time is on the order of seconds, while our scale of distance is on the order of meters, not hundreds of millions of meters. So what I'm going to do to kind of adjust that is to just kind of come into the graph settings here and just change the y-axis to I'm going to multiply it by a factor of 10, so 58.97 and 62.44, and look at things from the perspective of what things would look like from our perspective if just the speed of light was just 10 meters per second. And now you can see that the change in the horizontality of the dashed lines has almost no effect at all. But because the entire all of those horizontal lines are very, very nearly horizontal, so you can't even detect a difference in how much horizontal they are.